So I plan to discuss in this lecture 5 theorems. Okay. So first theorem is every chain is lattice. Okay. Prove that every chain is a lattice. So morning, I think the first lecture we discussed. Okay. So I think morning we discussed what the definition of chain and the definition of lattice. So chain means any two elements are comparable. So in okay, so suppose if you take A and B from the chain, A is less than or equal to B or B is less than or equal to A. So that's why we say that any two elements in a chain are comparable. Okay, I want to prove it is a lattice. Lattices means actually I need to prove uh, the least upper bound of A and B and the greatest actually this is actually greatest lower bound of A and B, and this is what least upper bound of A and B exist. So what you need to assume, what you need to prove, so that one it should be very clear. So x comma less than or equal to be a chain means if you take any two elements from x, they are comparable. They are comparable means either A is less than or equal to B or B is less than or equal to A. I want to prove this x, okay, comma less than or equal to is a lattice. So that means what I need to prove. So if you take any two elements, the greatest lower bound and the least upper bound exist. So that is I want to show that. Okay, now there are two cases. First case is what? A less than or equal to B. Second case is B less than or equal to A. Okay, so in this case, first case, A less than or equal to B, I am going to prove what? Uh, Greatest lower bound of A and B exists. Similarly, least upper bound of A and B exist. Okay, so please watch carefully the steps. It's not like a problem. Okay, if you miss any one of the step, you don't understand the proof. If you have any query, you can ask. Okay, so case one, A less than or equal to B. Okay, since we know that A less than or equal to A is always true. A less than or equal to B, that is given in the, that is a case. Okay, case one. Now this A, okay, which actually this A and this A, okay, both of them are same A. Okay, okay, this A is a lower bound of this A and this B. So A is a lower bound of A and B. So this is our next sentence. Okay, now the next, this equation 1 is coming from actually lower bound of, within bracket I need to write, here I don't write, lower bound of A comma B. Okay, you can write like this, lower bound of A comma B, okay, less than or equal to uh, I think yeah, lower bound, greatest lower bound of GLB, GLB of what? A comma B. So this is known because this is greatest among the lower bound. So the lower bound of A and B is what? The lower bound of A and B is A. So A less than or equal to greatest lower bound of A comma B means by notation it is what? A and B. This is the greatest lower bound of A comma B is A and B. So A less than or equal to A and B. So we got equation 1. Next, okay, next I will start again the proof fresh. Okay, since A and B is the greatest lower bound of A and B, so we know that A and B is the greatest lower bound of A and B. If it is a greatest lower bound, it should be a lower bound. So from here to here is implication. That's why implies A and B is what? Lower bound of A and B. Okay, so this quantity is a lower bound of A. Similarly, this quantity is a lower bound of B. So that's why this implies A and B less than or equal to A, because A and B is a lower bound of A. But similarly, it is a lower bound of B. That is, I don't need here. That's why I don't write here. So it is since A and B is a lower bound of A as well as is a lower bound of B. That's why A and B less than or equal to what? A. Now from equation 1 and 2, okay, here what? A less than or equal to A and B. Here A and B less than or equal to A. So we have A and B equal to A. So this implies greatest lower bound of A and B exist. Okay, that is equal to A. So we proved A and B, the greatest lower bound of A and B exist. Next, I will show the least upper bound of A and B exist. Okay. So for this, since the last proof I took A less than or equal to what? A less than or equal to A and A less than or equal to B. So here B less than or equal to B and A less than or equal to B is given. Now this B, okay, the right side B is a upper bound of this A and this B. Okay, now again you should use this relation, least upper bound of A comma B less than or equal to what? Upper bound of A comma B. So I'll write here LUB of least upper bound of A comma B less than or equal to upper bound of A comma B. So as here greatest lower bound of A comma B, I am writing what? A and B. Similarly, least upper bound of A comma B should write what? A or B less than or equal to what is the upper bound of A comma B? Upper bound of A comma B is what? B. So B. So I think A or B less than or equal to what? B. So that is equation number 3. Okay. Next, again I start from fresh. Since A or B is what? Least upper bound of A comma B. This least upper bound of A comma B I missed here. Okay. So A or B is least upper bound of A comma B. This implies A or B it is upper bound. Because it is a least upper bound, it should be upper bound of what? A and B. So this quantity is a upper bound of A as well as the same quantity is upper bound of B. So I am writing this quantity is here. It is upper bound for what? B. So that's why B less than or equal to what? A or B. It is also upper bound of A, but I don't need here. So from 3 and 4, we have A or B equal to B. So least upper bound of, actually this is the least upper bound of A and B exist. So already we proved greatest lower boundaries exist. Now least upper boundaries exist and hence L is what? Lattice. Next, case 2. So proof is very similar, okay, for case 2 also, but I will explain quickly. So here we need to assume what? The other way, B less than or equal to A. Case 1 is A less than or equal to B. Case 2 is B less than or equal to A. Okay, since we know that B less than or equal to B, this is always true, and this is by assumption, B less than or equal to A. Now this B, the left side B is a lower bound of this A and this B. So again here we need to write what? Here I have lower bound, so you should write a relation lower bound of A comma B within bracket as like this, lower bound of A comma B, okay, less than or equal to what? Greatest lower bound of within bracket A comma B. So the greatest lower bound of A comma B is what? A and B. The lower bound of A comma B is what? B. So B less than or equal to A and B. So this is equation number 1. Next, since A and B is a greatest lower bound of A and B, it should be a lower bound of A and B. It is a lower, this is a lower bound of A as well as lower bound of B. So I used only what? It is a lower bound of B. So that's why A and B less than or equal to what? B. So now from 1 and 2 we have what? A and B equal to B. This implies the greatest lower bound of A and B exist. And We need to prove next one, great least upper bound of A and B exist. Okay, so since A less than or equal to A and B less than or equal to A is given, that is assumption, that is case 2. Here, the right side A is an upper bound of the left side A and B. So this implies, again, here you have upper bound. The relation is what? The least upper bound of A comma B less than or equal to what? Upper bound of A comma B. The least upper bound of A comma B by notation A or B. Upper bound of A comma B is what? A. So that's why A or B less than or equal to A. Okay. Next, since A or B is what? Least, because of this symbol, is the least upper bound of A and B. It should be upper bound of A and B. So it is a upper bound of A as well as upper bound of B. I need here, okay, only it is upper bound of A only I need. I don't need here upper bound of B. So that's why A less than or equal to what? A or B is a upper bound of A. Okay, that's why A less than or equal to A or B. So from 3 and 4, A equal to A or B. So least upper bound of A and B exist. Already we proved in this case least upper bound of, sorry, greatest lower bound of A and B also exists. In this case already we proved, and hence L is a lattice. Actually, the proof is more or less all the lines are little bit very similar. Okay, wow. So once you understand the idea, you can easily write the proof. Okay, next, second theorem. Second theorem we will discuss about idempotent. Okay, so in the second theorem, we are going to prove idempotent law and absorption law. Let L comma less than or equal to be a lattice, then L satisfies the following laws. Idempotent law. Idempotent law means A and A. Actually, we don't read A and A. Actually, this is actually greatest lower bound of A and A equal to A. This is actually least upper bound of A, A and A. Okay. So for my convenience, okay, I'm reading this is R, this is and. Or you can read this is join, this is what? Meet. This is meet, this is join. Okay. So A or A equal to A. Absorption law, A and A or B is equal to A. Another law, this is actually dual of this one. So dual means instead of and you can replace R. So A or A and B is equal to A. Okay, we will prove one by one. We'll prove 1, 2, 3, 4. Okay. So L comma less than or equal to be a lattice, that is given the statement to prove idempotent law. So what is idempotent law? A equal to A and A. So I am going to prove, instead of proving directly this, A less than or equal to A and A. Similarly, the other way, A and A less than or equal to A. From 1 and 2, I am going to prove this. Okay. Since A less than or equal to A, similarly, I am writing A less than or equal to A. So all of them are same A, but for proof, we need to write like this. Okay. So this A, that is a left side A. Okay. Okay. This A is here. Left side A is a lower bound of right side A. This A and this A. Okay. Again, least, here we have where we are discussing about least upper bound. So least upper bound of A comma A less than or equal to greatest lower bound of A comma A. So what is the least upper bound of A and A is A. So I am writing here A less than or equal to, by notation, greatest lower bound of A comma A is what? A and A. Okay. Now I will take A and A. A and A is nothing but what? Greatest lower bound of A and A. So it should be a lower bound of A and A. It is a lower bound of A means A and A less than or equal to A. So from 1 and 2, we have A equal to what? A and A. Similarly, we need to prove A equal to A or A. So to prove A equal to A or A, again we need to prove A less than or equal to A or A and A or A less than or equal to A. Okay. So A or A, okay, is nothing but what? Is the least upper bound of A and A. Okay. So it is the least upper bound of A and A. It is upper bound of A and A. So this quantity is an upper bound of A means A less than or equal to what? A or A. So equation 3. Next, again A less than or equal to A and another one A less than or equal to A. The right side A. Okay, the right side A, this A is upper bound of the left side A, this A and this A. So again we are discussing about upper bound. The relation is what? Least upper bound of A comma A less than or equal to upper bound of A comma A. Least upper bound of A comma A means by notation A or A less than or equal to what is the upper bound of A and A is A. So that's why less than or equal to A. From 3 and 4 we have A equal to A or A. I think we proved idempotent law. Next, absorption law. Okay, there are again two of them are absorption law. So first we are going to prove A and A or B equal to A. So again the same idea. The idea is instead of proving A equal to B, A less than or equal to B and B less than or equal to what? A. Okay. So instead of proving this, equivalently we are going to prove the left hand side less than or equal to what? Right hand side. Similarly, the right hand side is less than or equal to what? Left hand side. Okay. So first we are going to prove A and A or B less than or equal to A. Okay. So here, okay, consider here this symbol and symbol. So that's why this represent greatest lower bound because of this symbol. Greatest lower bound of A and what? A or B. So it should be a lower bound. From here to here, just I am removing G, remaining everything is same. Okay, so it is a greatest lower bound implies it should be a lower bound. Okay, if it is a lower bound of A, this is a lower bound of A as well as lower bound of what? A or B. So I need only it is a this quantity is a lower bound of A. So that's why I wrote A. This quantity is here less than or equal to what? A, because it is a lower bound of A. Okay, but I don't need this is a lower bound of A or B. I don't need. Okay, this is equation number 1. Next, we need to prove the other way. Other way means A less than or equal to what? A and A or B. If I don't give the if I don't show the next slide, it is very difficult to predict what is the proof. If I show the next slide, you can easily understand the proof. I know that. So that is a problem in writing the proof. Okay. So you may think this is a little bit easier. Okay. For understanding, maybe it is easier, but writing the proof is slightly difficult, I feel, because you may forget the steps. Okay. Next one, to prove. Okay, the other way. To prove means other way means what? A less than or equal to what? A and A or B. So here, this point should strike out here. So you may know that we need to prove this, but the crucial part is this two. So then only you can proceed. Next step, next step, next step. Since A less than or equal to A, okay, and yeah, this is already we know that. Okay, this is always true. A less than or equal to A is always true. And A less than or equal to A or B. Why this is true means, okay, A or B is what? Least upper bound of A and B. So, and hence it is upper bound of A and also it is upper bound of B. So it is the upper bound of A. That's all over. That's why A less than or equal to A or B. Similarly, B less than or equal to A or B is also true, but I don't need that one here. Okay, now from here to here, this A, the left side A is a lower bound of the right side A and what? A or B. Next, again, here we are dealing with the lower bound. So, lower bound of A, comma, A or B less than or equal to what? Greatest lower bound of the same thing, A, comma, A or B. What is the lower bound of A, comma, A or B? Is A. So, A, left side A less than or equal to, again, greatest lower bound of these two means by notation, in okay, greatest lower bound means A, greatest lower bound means and A or B. Okay, this is equation number 2. Now from 1 and 2, what is 1? This is 1. This is 2. From 1 and 2, A and A or B equal to A. So we proved the first absorption law. Second one, okay, second one is actually, what is the second one? I will show the second one and then I'll come to the proof. Yeah, second one is A or A and B equal to what? A. Okay, so for this I need to prove again A less than or equal to A or A and B. Similarly, what? A or A and B less than or equal to A. Okay, I think up to this step we discussed. Okay, next, here A or A and B is actually what? Here R means least upper bound of A and what? A and B. It is a least upper bound means this should be upper bound of A and A and the same thing. Okay, A and B. Okay, now this quantity is the upper bound of A as well as this same quantity is upper bound of what? A and B. So it is an upper bound of A. That's okay. That only I need here. Okay, so this is equation number 3. Okay, next, since A less than or equal to A, that is we know. Okay, this is always true. Again, A and B less than or equal to A. The reason why this is true means this is actually what? Greatest lower bound of what? A and B. Okay, greatest lower bound of A and B. Okay, greatest lower bound of A and B. Actually, yeah, I'll write A and B less than or equal to what? A. So what is the meaning of this? GLB of A comma B. Okay, this is the greatest lower bound of, why this is true? Okay, this is actually what? Greatest lower bound of A comma B. So this implies it is a lower bound of what? A comma B. Okay, so this is actually lower bound of what? A as well as what? Lower bound of B. So that's why A and B always less than or equal to what? A. Similarly, A and B less than or equal to what? B. The reason is this quantity is the greatest lower bound of A comma B, and hence it is what? Lower bound of A as well as what? Lower bound of B. But I need only the first one. So that's why A and B less than or equal to A. Okay, this implies the right side A, okay, is an upper bound of left side A and B. Okay, now here we are dealing with the upper bound. Okay, least upper bound of A comma A and B less than or equal to upper bound of the same thing. So what is the least upper bound of A comma A and B? Actually, least upper bound means R. A and B less than or equal to upper bound of A and A and B is what? A. Now from 3 and 4, okay, 3 and 4 we have A and B equal to B. Okay, so from 3 and 4. Okay, so I think we proved absorption law also. Next, 3 equivalent conditions. Let L comma less than or equal to be a lattice. For any A comma B in L, the following are equivalent. Subdivision number 1, A less than or equal to B. Subdivision 2, A or B equal to B. Subdivision number 3, A and B equal to A. Okay, so here the following are equivalent means we are going to prove one, we are going to assume one, we are going to prove two. Similarly, we are going to assume two, we are going to prove three. Next, we are going to assume three and we are going to prove one. So, okay. So first assume A less than or equal to B. To prove what? To A or B equal to B. Okay. Now, to prove A or B equal to B, I am going to prove A or B less than or equal to B. Similarly, B less than or equal to what? A or B. Okay. Since this is by assumption, A less than or equal to B, and this is always true, B less than or equal to B is always true. The right side B, okay, because you have B and B, so that's why I'll take this B, is an upper bound of the left side A and the left side B. So here we are dealing with upper bound. So the least upper bound of A comma B less than or equal to upper bound of A comma B. Least upper bound of A comma B is what? A or B. Upper bound of A and B is B. So A or B less than or equal to B. This is equation number 1. We need to prove the other way. So since A or B is least upper bound of A and B, it should be upper bound of A and B. So this quantity is a upper bound of A as well as upper bound of B. But I need only upper bound of B only I need. So that's why I write B less than or equal to what? A or B. So from 1 and 2, 1 is what? 1 is A less than or equal to B, 2 is B less than or equal to A or B. So from 1 and 2 we have A or B equal to B. So next we should assume 2 and then we are going to prove 3. So actually 2 is what? A or B equal to B. 3 is A and B equal to A. Okay. So I will take the left side of equation 3, A and B, which is equal to A and B. B by assumption it is what? A or B. So that's why instead of B I replace what? Because assume A or B equal to B. So that's why B equal to A or B. A and A or B equal to A. Just now the previous theorem we proved absorption law. So A and A or B equal to A by absorption law. So the left side you have what? A and B, right side is A. So that is 3, subdivision number 3, A and B equal to A. So we proved 2 implies 3. Next, and then we are going to prove 1. So what is 3? A and B equal to A. 1 is what? A less than or equal to B. Okay. Since A and B is greatest lower bound of what? Because of this symbol is the greatest lower bound of A and B, and hence the same quantity is a lower bound of what? A and B. It is a lower bound of A as well as lower bound of B. I need only lower bound of B. That's why A and B less than or equal to what? B. Okay, but A and B by assumption by 3 A and B is what? A. So A less than or equal to B. That is subdivision number 1. Okay, we proved all the 3 are equivalent. Now we will use this one, the subsequent theorems. How we will use, I will tell you. So I think this is the smallest one. This is the biggest one. A less than or equal to B. R means the biggest one will come. Out of these two, which is the biggest? B. So and means the smallest one will come. The smallest one is what? A. So in this way, I will use this theorem later. Maybe in the next theorem also I'll use. So here sometimes they will ask state and prove isotone property. So you should remember the statement also. So if they gave the statement, okay, fine. Otherwise you should remember. So in any lattice, L comma less than or equal to the operations are and are isotone. So this is actually isotone property. So that is what they mean. If y less than or equal to z in L, then x and y less than or equal to x and z. So actually y less than or equal to z. Okay, that is assumption. X and y less than or equal to what? X and z. And similarly, x or y less than or equal to what? X or Z. For all x belongs to capital L. Okay, we will prove these two. By reflexive property, we know that x is less than or equal to x, always true. By idempotent property, x and x is equal to x. We know that idempotent property. So what is given the question statement y less than or equal to z is given. Okay. Now y and z, and means smallest one will come. Already I told you. Smallest one is what? Smallest one is y. Okay. So smallest one is y by theorem, previous theorem. Now I will take the left side. What is the left side? I am going to prove this one. Left side is what? X and y. Consider x and y. What is x? X is x and x. So instead of x, I will replace x and x. Instead of y, I am going to replace y and z. So, x is equal to what? X and x, and instead of y, y and z. Now everywhere you have and. Okay, wow. So I can use associative property. So a and b and c. I'll write a and b and c. From here to here, I used associative. From here to here, I am using commutative. X and y is equal to what? Y and x. Again, from here to here, I am using associative. A and B and C is equal to A and B and C. From here to here, I am using associative. From here to here, you should be listen carefully here. I am consider this is A. Okay, this is A. I think X and Y. This is also A. Okay, and this is something different. That's why I'll take B. So what you have here? A equal to A and B. So that is you have here. So when if it is and means already I told you the smallest one will come. So here here A and B equal to A means A is the smallest one, B is the biggest one. So from this we have by previous theorem, okay, A less than or equal to what? B. A is the smallest one, B is the biggest one. What is A here? This is A x and y less than or equal to what is B here? X and z. So that's why x and y less than or equal to what? X and z. So this is actually the first result. X and y less than or equal to what? X and z. Similarly, so if you have any doubt in this step, you can ask to me. Otherwise, I will go to the next. I'm going to prove x or y less than or equal to x or z. I'm going to prove. Okay, to prove this, I'm taking the left side. Okay, to prove this, I'm going to take the right side. Okay, right side is what? X or z. So I'm going to prove x or y less than or equal to what? X or z. Second one. Again, idempotent law. X or x is equal to x. So next, this is given the statement y less than or equal to z. So which one is a bigger? Z is bigger. If it is R means what? Y or Z means Z. In the previous case, Y and Z I used. So here the smallest one will come. Here in Y or Z means the biggest one will come. Again, this is by the previous theorem. Now, in the previous case, I took the left side. I already told you. Okay, to prove this one, I took what? X and Y. Okay. To prove the second one, okay, I'm going to take what? The right side, X or Z. So X or Z equal to X is equal to what? X or X, or Z is what? Y or Z. Again, everywhere you have R, the same idea. From here to here, associative. From here to here, X or Y is equal to what? Y or X, commutative. Again, from here to here, I'm using associative. The same idea as in the previous case. Okay. So once I got this, I'm take this is B. The same B is here. X or Z is B. This is A. So B equal to what? A or B. So so A or B equal to B means, so B is the biggest one, A is the smallest one. So A less than or equal to B. So what is A? X or Y less than or equal to X or Z. So that is I want to show. Okay, dual statement. In any lattice L comma less than or equal to, the statement A comma less than or equal to B implies A or B equal to B is valid. Okay, hence it's dual statement. So dual statements means instead of less than or equal to, replace greater than or equal to. Or means replace R by and. So the dual statement A greater than or equal to B implies A and B equal to B is also valid. So that is a dual statement. Using this dual statement, we are going to prove the next theorem. Okay. So this is the last theorem in this lecture. So the elements of an arbitrary lattice L comma less than or equal to satisfies the following inequalities. Sometimes they will ask state and prove distributive and modular inequality. So you should remember all the four inequalities again. So distributive inequalities XR, Y and Z less than or equal to XR, Y and XR, Z. Second one, it's a dual. Okay, dual is what? Instead of R replace and instead of and replace R. Less than or equal to means here greater than or equal to, and na R and R and. So once I proved this by using dual, okay, this is true, this is also true. Next, modular inequality. Whenever x less than or equal to z, x less than or equal to z, xr, y and z less than or equal to xr, y and z. Actually, fourth one is the dual of third one. So less than or equal to, instead of less than or equal to, we have greater than or equal to r and r, less than or equal to, here greater than or equal to r and r. So now I am going to prove only one, first one. So first, once I proved one, from using one I am going to prove three. Once I proved 1 and 3, 2 is a dual of 1, 4 is a dual of 3. So using dual statement, we will prove 2 and 4 easily. So first one is, you should know the proof of the first one. Okay. So first we need to prove XR, y and z less than or equal to what? XR, y and XR, z. Okay. Since x is less than or equal to XR, y, already I told you XR, y is what? Least upper bound of x and y. So it is the upper bound of x and y. So it is the upper bound of x. It is the upper bound of y also, but I don't need here. So it is the upper bound of x. Similarly, XR, x is less than or equal to what? XR, y. Same reason. Okay. Now, this left side x, okay, here I have x and x. The left side x is a lower bound of the right side XRY and the right side what? XRZ. Next step, you need to write, okay, because we are dealing with what? Lower bound. So the same idea. Lower bound means what you need to write? Lower bound of not a comma b. What here you have? Here you have XRY comma XRZ. XRY comma XRZ. Less than or equal to GLB of XRY comma XRZ. So here by notation, what is this? XRY, GLB means and XRZ. What is the lower bound of XRY and XRZ? Lower bound of X. Okay, that's why we have this inequality. So X less than or equal to what? XR y and XR Z. Okay. Now, from this equation, the right side quantity is an upper bound of left side quantity because x less than or equal to this. That's why this is an upper bound of this x. Okay. This is the first result. So, uh, similarly, we are going to prove actually what we proved this quantity. This is same as what this. This quantity is a upper bound of x. Similarly, we need to prove this quantity is a upper bound of what y and z. So for this, consider y and z. So y and z less than or equal to y. The reason is it is the greatest lower bound of y and z. It is a lower bound of y as well as z. It is a lower bound of y. So that's why y and z less than or equal to y. Y less than or equal to what? X or y. What I told already, x less than or equal to x or y. Similarly, y less than or equal to what? X or y. The same idea from this side. Y less than or equal to x or y. Next, y and z less than or equal to z as in the first inequality. Okay. Instead of okay, y and z less than or equal to z is less than or equal to what? X or z. Okay. Now, the left side is same. Okay. Wow. Here also what? Left side is same. X. So here left side is same. So this quantity is a lower bound of what? The right side quantity x or y and x or z. So now here we are dealing with the lower bound. So lower bound of lower bound lower bound of x or y comma x or z less than or equal to GLB of the same thing x or y comma x or z. So less than or equal to right side is GLB, that's why x or y. GLB means and x or z. So what is the lower bound of these two? The lower bound of these two is y and z. So y and z less than or equal to this. So we'll check it in the next slide. Yeah, y and z is less than or equal to x or y and x or z. So this implies, okay, so this implies the right side quantity is an upper bound for the left side quantity. So is an upper bound of y and z. So already I told you in the previous slide, we need to prove this is upper bound of x. Already we proved the right side quantity is upper bound of x. Similarly, the right side quantity is upper bound of what? Y and z. That is also we proved. So this implies the right side quantity. What is the right side quantity? X or y and x or z is an upper bound of x. It is an upper bound of x, and also it is an upper bound of what? Y and z. Okay. Next, again we are dealing with the upper bound. So what you need to write? Least LUB of two quantities less than or equal to upper bound of two quantities, the same two quantities. What is the quantity here? Okay, the quantity is x comma y and z. X comma y and z. Here also what? X comma y and z. Least upper bound, that's why x or y and z less than or equal to, what is the upper bound of these two? Upper bound of these two is what? It is given, it is we derived x or y and what? X or z. X or y and x or z. Okay. So actually this is nothing but distributive inequality. So please check it. So x or y and z, that is the left side. Right side is what? X or y and x or z. So okay, so you need to okay, first I will tell you After finishing this lecture, I will tell you somewhat. Okay, so you people remember the proof easily, but anyway, just I will give you some hint. Okay, so and hence distributive law is true. Okay, now the inequality 3. Okay, the inequality 3 is a special case of what? Inequality 1. Okay, so inequality 3 is a special case of inequality 1. So here you need to assume what? X or Z. Okay, X, sorry, X less than or equal to Z, you need to assume. So this is true means I will prove the first one. So let us assume this is true. Left hand side of 1 and 3 is same. Okay, X or Y is also same. Only thing under X or Z, X or Z, X or Z is what? Which one is a bigger? Because R. So the bigger one is what? Z. That's all. Proof is over. Okay. So you need to write first this one, and you should use X less than or equal to Z. You will get this inequality. So okay, again I'll explain here. The inequality 3 is a special case of inequality 1. So in inequality 3, it is given if X less than or equal to Z, then X or Z means bigger one will come. Bigger one is what? Z. So now from 1, this is 1. From here to here it is 1. Okay, X or Y and Z less than or equal to what? X or Y and X or Z. Okay, but this is equal to X or Y. X or Z is what? Z. So now this is 3. What is 3? 3 is actually X or Y and Z less than or equal to what? X or Y and Z. So please check it. X or Y and Z less than or equal to what? X or Y and Z. So which is the inequality 3. Okay, now already I told you apply dual statement. We get 2 from 1. We'll get 2 from 1. Dual statement is what? This is the dual statement. So we get 2 from 1. Similarly, apply dual statement. Okay, we get 4 from 3. 4 from 3. Because fourth one is a dual of what? The third one. Okay, so I think we discussed 5 theorems, but theorems are slightly I know that. Okay, for the students like computer science students, okay, SOC students, little bit difficult to remember, but you need to do for at least for exam point of view. Okay, so the idea is first you should remember these result. So what you need to assume, what you need to prove. For example, for preparing the exam, suppose if I want to prove this is less than or equal to this means, so you should remember the key points. I want to prove, okay, this should be an upper bound of X. Similarly, we need to prove this is upper bound of what? Y and Z. Similarly, those key point you should, if you remember, okay, in each of the proof, then you can write, okay, uh, you can write the proof. So that is my suggestion. If you have any other plan, okay, you can go ahead. Okay, thank you. If you have any doubts, you can ask me. Otherwise, we will discuss the rest of the topics tomorrow if I have enough time. Okay, if there is no doubt means you can leave.